Today we're going to be looking at making a ring light for a 3040 router. Although this could be adapted to almost any desktop router or other CNC machine. The corner of my basement where my route is installed is very dark and it's hard to see what I'm working on. Let's take a look at the schematic. Don't worry if you can't read all the details here. The files will be all included in a PDF that you can download below. The ring light has 11 LEDs arranged in series with a transistor connecting it to ground. The transistor acts as a constant current source to pull about 15 to 20 milliamps through the LEDs, keeping them bright but not overloading them with current. The circuitry to the left of the LEDs is a DC converter. Since the LEDs require about 35 or 36 volts to operate, the DC converter steps up the 12-volt battery to 36 volts for this purpose. To the left of the DC converter is a voltage regulator, in this case a 12-volt regulator, in case you're running a higher input voltage. The integrated circuit used for the DC converter is limited to a maximum of 14 volts, so the 12-volt regulator may or may not be necessary depending on the source of DC power. Now use your favorite PC board layout software to convert the schematic into a circuit board. Here's the printed circuit board layout for the circuit shown on the schematic, including the voltage regulator, which you may or may not want to use. Note that it's arranged in a circle with an inner diameter that is slightly larger than the spindle on my machine, and an outer diameter whatever it takes to fit all the components on the board. The red traces on the layout represent the copper on the top of the circuit board. The next step is to import the circuit into your favorite CAD program, and then we're going to pull a trick that I've used on a number of circuit boards. Here's a close-up of part of the board. Note that one end of the RE1 is connected to one of the terminals on Q1, the transistor. This is the only connection between these two pads. Note there are white lines drawn on the board surrounding that pad area. They may be a little hard to see here. That red line that we were looking at represents this connection as shown on the schematic, connecting the emitter of Q1 to one end of RE1. Here's the same connection with the red line removed between the two pads, and the white lines showing the ones that I drew with the CAD system surrounding those two pads. The object is to draw lines around all pads that are connected together, isolating them from all other pads that they are not connected to. Once the lines are all drawn, I use my CNC router to engrave the lines that I just drew. This cuts the copper, leaving isolated copper traces, the size and shape of the rectangular area that we drew. Once we have the board done, we will solder components straddling the lines. This is a surface mount resistor. This resistor is a 100 ohm RE1 that was shown on the schematic. I know it looks like 1,000, but that's the designation for a 100 ohm resistor. It's the number 100 followed by 0 zeros. If it was 1003, it would be a 100 k ohm resistor. That is 100 followed by 3 zeros. Note that the resistor is centered on the line, straddling the gap between the two pads, and each end of the resistor is soldered to one of the pads. Here is the completed board with all the lines drawn, isolating all of the areas that are not connected together. Now go into your favorite CAM system, in my case I use BobCAD, to convert the CAD drawing into something that you can use on your router. First step is to drill mounting holes in a piece of rectangular circuit board material. Since I don't have a tool changer, I created 4 separate files for completing the board. First for drilling the mounting holes, then for drilling holes for the through-hole components, next for engraving the lines drawn with the CAD system, and finally profiling the outside and inside of the board itself. All of the lines that we drew on the previous drawing will be engraved with a pointed tool bit going just deep enough to cut through the copper surface, in my case about 10/1000ths of an inch deep. I'm using a tapered cutter for the operation, and the cuts that are made are about 10 to 15 thousandths of an inch wide. For this to be successful, the board has to be mounted on a plate, which is a sacrificial plate, in this case plastic, and the plate has to be very level relative to your tool bit so that the lines are consistently cut over the entire area of the circuit board. In my case, I mounted the plate on the machine and then fly cut the surface to get it as flat as possible. Also note that I have 5 screws in the center of the board, which is an area that will be thrown away, holding down the circuit board while I'm engraving it. Here's the completed engraving job showing all the lines that have been cut, representing the lines that we showed on the earlier CAD drawing. Note the mounting holes around the perimeter of the ring that do not have screws in them at this time. These screws were intentionally left out to avoid hitting them with the engraving bit or the drill bits when drilling the holes for the through-hole components. The next step is to go in and cut a profile to remove the excess material in the center of the ring and around the outside. For this operation, it will be necessary to install screws in at least some of the mounting holes around the perimeter so that both pieces of the board will be supported once they are cut apart. Here's a close-up showing one of the screws added in the perimeter of the ring. Once completed, the circuit board is cleaned up to take off any burrs with some 500 grit wet or dry sandpaper, just lightly sanding it enough to give a nice shiny surface to the copper and remove burrs around all of the cuts done by the engraving. The finished board is now nice and shiny and ready to be cleaned and assembled. The first step is to use some soap and water and a toothbrush to clean out any tiny bits of copper that may be embedded in the lines that we engraved, so we don't short any pads together that are not supposed to be connected. Next, we want to put some solder coating on the board in order to give it some corrosion protection. You could solder plate this before you engrave it if you have the capability, or tin plate it if you wish. For my purposes, I put a thin layer of solder on using my soldering iron before I put the components on. To do this, I take some 91% isopropyl rubbing alcohol and a few drops of rosin core soldering flux and mix them together to make a dilute flux solution. A small amount of this is mixed up and put on with a Q-tip, covering the copper surface of the board. Once the flux is on the board, take your soldering iron and a tiny bit of solder and just rub it over the surface, enough to coat the surface with solder, but not enough to fill up the holes or the gaps between the pads. Once the board is completed, I clean off the excess flux using a paper towel and some rubbing alcohol. Now we can solder all the components on the board, carefully straddling the lines that are cut, making sure that the metal pads on the end of the components do not short against adjacent pads where they are not supposed to contact. Note, looking back at the circuit board layout, I had to put a couple of traces on the back side of the board in order to make all the connections that I needed. These are connected with through-hole vias between the top surface and the bottom surface. They are represented here with the blue lines shown on this layout. Since I'm using a single-sided PCB, the jumpers on the back side are accomplished by soldering wires into the holes provided. Next, a flexible grommet is 3D printed using flexible plastic. This grommet has a ring in it to fit inside the circuit board and with the inside diameter to be a snug fit on the spindle of the machine. This is why the inner circle was cut slightly larger than the spindle to accommodate this grommet. Here the circuit board has been installed on the spindle, and again note that the flexible grommet that we made prevents the electrical components from touching the spindle. Here's a little larger view of the circuit board attached to the spindle. In my case, I'm using a battery to power the lights. The battery is velcroed to the spindle of my machine. One thing you may want to do is add a switch to your circuit. In my case, the black and white wire pigtail coming off are intended to be used for a switch for turning the light on and off. Now I can really see what I'm working on when I'm running my machine in that dark corner of the basement.